I hope everything is good. I already uploaded the slides that we are going to discuss today. I hope we are fast enough for you to see clearly. So today we will start with new topic that is called MOSFET. So this term MOSFET has is a combination of two different terms. One is MOS, another one is FET. First, we will discuss about MOS, the term MOS. The term MOS came from uh, MOS gap. So let's try to understand what is MOSFET. And in order to understand what is MOSFET, we have to understand the concept of parallel plate capacity. In your basic physics course, I think you already learned about this concept of parallel plate capacitor. In this diagram, we have two metal plates, one at the top, one at the bottom. And in between, we have another material called insulator. Insulator is such material that does not flow any or the resistance is infinite. And metal is such material that can flow current and the resistance is ideally zero. These two metal plates are separated by a distance of d. The metal at the top is called top metal and the metal at the bottom is called bottom. And the area of each of the metal plates is A. Capacitance of this particular structure is given by C is equal to epsilon H that epsilon is the dielectric constant times A area of the metal of each of the metal and the D is the distance between these two. Another equation for capacitance is Q divided by D. Now this Q is the total charge of each of the metal plates and D is the voltage applied across this capacitor. If we rewrite this equation, we can write Q is equal to C V. Now C is defined by dielectric constant, area and the distance. Dielectric constant is a universal constant. A is the area of the metal. For a given structure, A is constant and D is the distance between this metal, and for a given structure, D is also constant, which means C is a constant because all the terms in this equation are constant. So as a result, C is the constant. Now if we take a look at the simplified view of this parallel plate capacitor, top, bottom, cylinder in which we have a voltage. Anyway, we can actually continue discussing. So first of all, if we apply a certain voltage, that voltage,
Sir,
there will be
the
some,
sound is not clear.
okay. So is it volume is low or noise?
Sir, volume is low actually.
Okay, so let me try it. All right, if we apply, is it better now?
Yes, sir, it's better now.
Okay. If we apply a certain voltage, V, and for that particular voltage, there will be some positive charge at this terminal and there will be some negative charge at this terminal. And those are identified with this black color. And for that particular voltage and charge, there will be certain positive charge at the top plate and certain negative charge at the bottom plate as defined by the black color. Now, if we increase the charge and add some blue uh, positive charge and blue negative charge, the top metal will get more uh, blue positive charge and bottom metal will get some blue negative charge, which means that as you can see, that in the charge depends on the voltage directly. If we increase the voltage, the charge on each of the plate will increase also. So if that's true, if that is true, that we and C is constant, uh, as a result, charge is directly proportional to the voltage. If we increase the voltage, charge will also increase. Now, what will happen if we decrease the if we decrease the voltage and apply a negative voltage, similar to this previous situation, if we apply more negative voltage, there will be more negative charge at the top metal and more positive charge at the bottom metal as defined by two different colors, black and blue, which means that the charge is proportional to the voltage even in the even for the negative voltage. So in summary, we can say that the Q charge, the total charge on each of the plate is directly proportional to the voltage and also exactly identical to the voltage. If the voltage is positive, charge will be positive. If the voltage is negative, charge will be negative. We already discussed that C is constant for a given structure and V is the external voltage and it is also known. So this is the fundamental uh, property of a parallel plate capacitor. Any question from this side? So these are very important concept. You should know this already, but I'm going through it one more time because this is very important concept for most to understand the operation of most. Okay. If there is no question, I think we can go to the next slide. From the previous page or slide, we saw that charge is directly proportional to the voltage. Now, if we change the voltage, the charge will also change. So this is an important thing. The change of charge concentration by external voltage. So there are two things. One is change of charge concentration. Another item is external voltage. If you recall, the objective of this course was to modulation of charge carrier, modulation or change of carrier or charge. So this statement is identical to this statement. That means for a parallel plate capacitor, we can change the number of charge or charge concentration by applying external voltage. So this that means the parallel plate capacitor is an important topic for this course because it directly represents what we are trying to achieve. Now, if that is true, we can build a capacitor that can be used to change the charge concentration by external. So we can change the charge concentration and change. If we do not do anything, there will be no change, right? So what do we need to do? We need to change the external voltage. So we can change the charge concentration by external voltage in a capacitor. So we are building the building our story. So we are building the concept to for the final device that we will. Now the basic concept that we discuss is with two metal plates. But in semiconductor, we have to use the semiconductor for part of the structure of the device, right? Like the diode, we used N-type silicon, P-type silicon. So if we do not use semiconductor, that it will not be a semiconductor device. So if we want to develop a semiconductor device, we have to use a semiconductor metal. So how can we build a parallel plate capacitor with semiconductor, especially silicon? For example, silicon. We can use different types of semiconductor, but for this course, we focus on silicon only. Now, one of the basic principle for a semiconductor device is that the bottom material must be a semiconductor. In a semiconductor device, the bottom material is always a semiconductor. For this case, for our course, we will use silicon. And for insulator, if we want to build a capacitor, we need a insulator. That insulator, the insulator that we use for semiconductor, mainly silicon dioxide. There are other insulators also, but we will focus on silicon dioxide. And for the top material, we can use any kind of metal, especially aluminum and copper. So if we combine all these conditions, then we can build our basic structure, basic semiconductor parallel plate capacitor, and that will look like this. At the top, we will have metal. At the center, we will have insulator, which is silicon dioxide. And at the bottom, we will have silicon, mainly P-type silicon. So how does it represent a parallel plate capacitor? Because we know from the basic concept, a parallel plate capacitor must have two parallel metal. In this structure, we have one metal at the top. We also have an insulator, but the bottom is not a metal. It's a P-type silicon. For a pure silicon, the resistance is very high. Ideally, it's infinite. But if we add P-type material, P-type doping, the resistance decreases. So we can approximate this P-type silicon as a metal. If we approximate this P-type silicon as a metal, then this structure becomes a parallel plate capacitor. Any question?
No, sir.
Okay. The next page. So as we mentioned earlier, that our objective is to modulate the carrier. And in this particular case, if we use a capacitor, then we will have to modulate the carrier by voltage, by applying voltage. So now we have to prove that this structure, we can modulate the carrier by this structure. So we have two structure. One on the left we have parallel plate capacitor, top metal, insulator, bottom metal. Another one is MOS capacitor. By the way, so why do we call it MOS? So at the top we have metal M, insulator is an oxide O, and at the bottom we have semiconductor S. So these three terms combines together as MOS, M-O-S, MOS. So here on the left we have parallel plate capacitor, and on the right and center we have MOS capacitor. On the right we are applying a voltage. So we are applying same voltage for the parallel plate capacitor and also a MOS capacitor. Now we are going to analyze how we can modulate the carrier by changing the voltage. So we will do this analysis in like total of five different regions. So the very first region is when the applied voltage is less than zero, or the applied voltage is negative. If the applied voltage is negative, that means this terminal will have negative charge, this terminal will have positive charge. For the parallel plate capacitor, when we apply negative voltage, top plate will get negative charge and the bottom plate will get positive charge. Okay? Bottom plate will get positive. Now, here we have two plots, one for parallel plate capacitor and one for MOS capacitor. So for the parallel plate capacitor, for both capacitor, we are going to plot the charge at the bottom plate versus the voltage. When we apply negative voltage, we have positive charge at the bottom plate. So that is defined. This, I guess, this is red. This color red. So we have negative voltage, positive charge at the bottom. Negative voltage, positive charge at the bottom plate. So I tried to match the color, so that way it will be helpful for you to visualize. Does it make sense? When we apply negative voltage, the bottom plate will have positive charge, right?
Yes, sir. Yes, sir.
Okay. Question. So let me move to the next set of slides. And so next we'll move to define the MOS structure. We already understood the MOS capacitor structure. Now we will try to build a MOS FET. So from our previous discussion, we saw that charge the the charge at the bottom plate versus the applied voltage looks like this. At this point, when the charge is zero, is called the threshold voltage, and this is the basic structure of a MOS capacitor. So, the if we want to write a mathematical equation for this for the charge at the bottom plate, it should look like this. So it's a kind of a straight line. QB is equal to minus M, that is the slope. V is the applied voltage plus C, the charge at the zero. So this Q is the total charge on each plate. So if the charge of one carrier is Q, the total charge will be given by NQ. So this factor is very it should be everyone should be familiar with this factor NQ. We always write this equation. So we can modulate the charge, which is so the I think we already explained we cannot change the charge of an insulator. We cannot change the charge of uh, in a metal. We can only change the charge number of carrier in the semiconductor material. So change of carrier is a semiconductor effect. Now by external voltage. So external voltage is a capacitor effect. Okay. So that means we can change the we can change the carrier concentration by applying voltage. Changing charge is semiconductor effect, and external voltage or applied voltage is a capacitor effect. Now, if we can do that, that means that if we can write the equation J is equal to NQV. So this is a very familiar equation for us. Now NQ is the QB, and we already proved that we can change the number of carrier by applying external voltage. So if we can change NQ, value of NQ, that means we can change the value of J also, current density. And we can change the NQ by applying voltage. So that means we can change the current density by applying voltage. And we can do it with this MOS capacitor. Is it clear for everyone?
Yes, sir. Clear, sir. Sir, in here, J is the current, N is the number of charges, Q is the charge
Do you have a
value.
question? Again, maybe I'm not sure what's going on, but can you write your question in the message box or chat box? Very good. Or if you do not have any question, just write no question. How? This is current. J is the current density. This is voltage, and we can say MV is is equal to resistance. MV is equal to resistance, and minus sign, we have minus sign here because of the electron. We are considering electrons only. That's why we have minus sign. So if we apply the value of electron here, or the value of Q minus 1.6 10 to the 19, this negative sign will go out. So that then we will have exactly identical Ohm's law. Current is equal to voltage by resistance. Sorry, actually MV will be conductance, and inverse of NV will be resistance. Any question about the interpretation of this equation? All right. So now we have to make sure that we can flow the current. And we will see what kind of a structure will we should use to be able to flow the current. So why I'm saying it, we are already modulating the carrier. So why there is a question of current? So let's see. So in this capacitor structure, we have this MOS capacitor structure where we applied the voltage between top metal and bottom metal, and we have an insulator in between. If we have an insulator in between, what will be the current? I think everyone knows it, and because of audio issue, let me answer the question. If there is an insulator in between in the path of the current flow, the current flow will be zero because insulator will not allow to flow any current. So we can modulate the carrier, but we cannot flow the current, unfortunately. So the, this modulation has no use, no effect. So how can we use this property of modulation to flow current? So let's see. All right. So I think I already discussed it, but current cannot flow because there is an insulator. So what is the benefit of this modulation? Current cannot flow vertically because of insulator. Obviously, there is an insulator, so current cannot flow. But all right. Now we have an insulator in the vertical direction, but we do not have any insulator in the horizontal direction. So in the horizontal direction, we only have a P silicon. So let's see if we can use the horizontal direction to flow the current. So and then we will try to build our structure, and we'll do it by some trial and error. Now the first combination that we can do, we can add a P type silicon on the left side and also on the right side, and apply a horizontal voltage. So now we will have two voltages. One is vertical voltage and one is horizontal. Why is it vertical? Because it is applied vertically. This is horizontal because it is applied horizontal. And we will divide this entire region into four different sections. The region under the oxide, and the region at the bottom side of the P silicon. Left P is number 3, right P is number 4. And again, we have this kind of plot for the bottom plot. This plot is very important. If you understand this plot, you understand MOSFET. All right. So when we build a transistor, we know the transistor can be used as a switch. That means we should be able to flow the current, or able to control the flow of the current. So the condition is only charge modulation will be allowed to will allow current flow. So only charge modulation will we will use the charge modulation to flow the current, to control the flow of the current. So let me try to explain what it means. So if we look at this structure, we have P, P, and P. So all are same kind of metal, which means there will be no junction. This region 3 will can be represented by resistance. Region 2 can be represented by resistance. Region 4 can also be represented by a resistance. But what will happen for region 1? As we discussed earlier, the the charge for the region 1 or the bottom plate can be positive or can be negative. So we don't know. The charge in the bottom plate or region 1 can be positive or 0 or negative. So if we do not know the property of something, that is not reliable. We cannot use it for our benefit. So we cannot rely on the region 1. As I mentioned earlier, the section 2, 3, and 4 all are p-type matrix. So when we apply a voltage across the same type of material, what will be the current? The current will be voltage divided by the total resistance of the path. So equivalent resistance will become a voltage source and three resistance in series. I should have drawn that equivalent circuit here, but anyway, I think you get the idea. Now, if we have a circuit with a voltage source and three resistance only, can we change the value of the current? Because these three resistance are fixed, voltage is fixed. Is there any way we can change the current? So we have constant resistance, constant voltage. What will be the current? Constant or variable?
So constant, sir.
It's
Right,
constant for me.
constant. So for this structure, we can see that there will be current flow, of course, but we cannot change the current. But for the condition, it has to change or modulate. We should must be able to modulate or change the current. That means this structure, I think I this is not this is wrong statement. It should be condition not satisfied. Okay, so we should correct this one in your note. The condition not satisfied. So if the condition is not satisfied, we cannot build a MOSFET with this structure. Any question?
No,
No,
sir.
sir.
Okay, good. So let's go to the next combination. Next combination, we have P in the center, P at the right, but N type silicon on the left. So if we draw a equivalent circuit, so when we apply negative vertical voltage, so charge will be the bottom charge will be positive as defined by the uh, red red color, and the equivalent for the red color charge is should look like this. We have a resistance from P, resistance from P, there is a junction, and resistance from N. So in this particular structure, the can will current can flow only in this direction, in the from right to left. Okay? But we cannot flow the current from left to right because of this diode. Even if we modulate and make the charge in this area, in this red area, negative, there is no way we can flow the current in the opposite direction. That means the flow of current does not depend the modulation of the charge. Let me try to explain one more. The charge in this particular area, the red area, can be positive or negative. If the charge in this red area is positive, this is the equivalence. If the charge in the negative, if the charge in the red area is negative, this will be the equivalent circuit because if we have a negative charge here, the junction will shift from left side to the right side. So there will be two parallel plugs, one at the top and one at the bottom. But no matter which way we go, we have a diode in, from right to left, right to left. And here we also have a diode from right to left. So the current can only flow from right to left. So it has nothing to do with the modulation of the charge. The flow of current is controlled by the diode, not by the modulation of charge. This diode and this two diode will only allow to flow the current from right to left. So the current is controlled by this diode, not by the modulation of the charge of the MOS capacitor. So if that is true, is the condition satisfied?
No.
No, sir.
Right. So the condition will not be satisfied because the current is not controlled by the modulation of the charge. Current is controlled by the diode or the charge. Anyone has any other question? All right. Let's go to the next combination. The next combination is just same as second one, but in this case we have N type on the right side and the P type on the left side. So the current will be able to go from left to right, but not from right to left. And if that is true, that means this condition is also not satisfied. The the flow of current will be controlled by the diode, not by the modulation of the charge, just like the second combination. Make sense?
Yes, sir.
Yes, sir.
All right, good. So now we have only one combination left, where we have N on the both N on the left and right side. And here we also divide the entire section into four different regions: section 1, section 2, section 3, and section 4. Now, if we draw the equivalent circuit of this structure, when the vertical voltage is less than threshold, if the vertical voltage is less than threshold, that means we have positive charge here. At the bottom plate, we have positive charge, right? So we have negative charge, positive charge, negative charge. So that means we have one junction here and another junction. You can see this circuit, this equivalent circuit. This equivalent circuit, we have two back-to-back diodes. So for this condition, vertical voltage is less than threshold. No flow of current because of back-to-back diodes. But if we apply vertical voltage which is greater than threshold, then we will have negative charge at the bottom. We have negative charge here, negative charge here, negative charge here. What will happen? We have same kind of material from left to right. So we can write the equivalent circuit, one resistance for this, resistance, and a resistance. So now if we apply voltage across this resistance combination, there will be current flow, right?
Yes,
If
sir.
we have only three resistance and the voltage source, there will be current flow. Make sense?
Yes, sir.
I don't hear any answer, so response. So
Yes,
you
sir.
must have some
Yeah.
question.
Yes, sir. I already said yes, sir. I mean,
Okay, I cannot hear you right now. Oh, good. Okay, so now we can see if we conclude this what we have in this picture. That means if we apply a voltage which is less than threshold, the current is zero because of back-to-back wire. But if we apply a voltage which is greater than threshold, there will be current. So see, now we satisfy the condition. How? We apply the external voltage. As a result, there will be modulation of the charge, and because of the modulation of the charge, we can control the current. So the condition is satisfied. The condition was, if you recall, the condition was the current only the charge modulation will allow current flow. So what we did here, we apply different voltage. Applying different voltage, we modulate the charge, and because of the charge modulation, we can control the current in this device. So that means this is the right, correct structure of a MOSFET. Any question?
No, sir.
Okay, very good. All right, so I think that's the last slide I had for today. I will stop here. Trying to I will share it in our Google Classroom.